Since the movie's release in 1999, The Matrix has had an overwhelming amount of positive reviews. However, my partner and I have chosen to give The Matrix its first physics review. Many of the scenes are fictional. One in particular scene stood out. We will focus on the part in the scene where Neo attempts to jump from one building rooftop to another. Morpheus, Neo's mentor, demonstrates first as he leaps to the other rooftop with no difficulty. Neo is in shock as he watches Morpheus land safely. Neo clears his mind and attempts to make the jump. As expected, Neo freefalls straight onto the pavement below. In the scene, Neo survives the fall with no injuries. With careful calculations and estimations, we plan to not only demonstrate the fall Neo survived would not be humanly possible, but that the jump Morpheus achieved would not likely be possible as well.
I will first focus on the calculations for the first section of the scene where Morpheus demonstrates projectile motion. After reviewing the scene several times, we have estimated the two buildings to be roughly 60 feet or 18.2 meters apart. We have also estimated the angle at which Morpheus jumps to be about 60 degrees. With these estimations, I can now begin calculating his initial velocity. We can start to calculate his initial velocity by using the square root of the range times gravity divided by the sine of 2 times the angle. If we plug in our numbers, we'll have the square root of 18.2 meters times 9.8 meters per second divided by the sine of 2 times 60 degrees. This will give us an initial velocity of 14.35 meters per second. Now we need to calculate his velocity in the x and y direction. To find his velocity in the x direction, we can use the equation initial velocity times the cosine of the angle. Plugging in our numbers, we can do 14.35 meters per second times the cosine of 60 degrees. This gives him a velocity of 7.2 meters per second in the x direction. For the y direction, we can use the same equation plugging in sine this time. So we have 14.35 meters per second times the sine of 60 degrees, giving him a velocity in the y direction of 12.4 meters per second.
After estimating the jump Morpheus achieved of 18.2 meters, we are curious to see if someone with training, such as an Olympic long jumper, could achieve a jump of such great length. In 1991, Mike Powell of the U.S. leapt 8.95 meters at the World Championship in Tokyo. This record is a remarkable length for a human to jump, but the jump Morpheus achieved was estimated to be even greater.
Morpheus ran off the rooftop with an initial velocity of 14.35 meters per second, which is extremely large. We compared his velocity to the recorded velocity of world record holder Usain Bolt, who has reached a maximum speed of 10.44 meters per second. If Morpheus did start with a velocity of 14.35 meters per second, he would have passed Usain Bolt right by.
We can now mathematically infer that Morpheus could have made the 18.2 meter jump only if he maintained both the x and y velocities while in the air. However, world records today lead us to believe this jump is in no way possible for a human being with even the greatest skill and training.
To determine if a human being will be able to survive the free fall Neo walked away from, I must estimate a few variables. I have estimated the building Neo fell from to have a height of 182.8 meters and Neo's weight to be 79.4 kilograms. I have chosen to use the law of conservation of energy to find his final velocity. This law states the sum of the initial kinetic and potential energy should be equal to the sum of the final kinetic and potential energy. The final velocity is equal to the square root of 2 times the acceleration of gravity, 9.8 meters per second squared, times the height of the building. This equation makes Neo's final velocity equal to the square root of 2 times 9.8 meters per second squared times 182.8 meters, giving Neo a velocity of 59.86 meters per second. I can now solve for the change in the kinetic energy. The initial kinetic energy of Neo at the top of the building would be 0, and the final kinetic energy can be solved using 1/2 times Neo's mass times his velocity squared, or 0.5 times 79.4 kilograms times 59.86 meters per second squared. This calculation will give Neo a total of 186,826.6 joules. Looking back to the previous calculations, I am able to find the force Neo hit the pavement with. I will divide the kinetic energy by the distance Neo traveled after hitting the concrete. I don't know for certain the distance Neo traveled after impact, but I have estimated it to be 0.001 meters. The average force of impact will then equal 186,826.6 joules divided by 0.001 meters, equaling a force of 186,826,612 newtons.
Breaking or cracking a bone depends on how quickly a force is applied to it. A quick force of about 3,000 newtons applied to the body has a 25% chance of cracking most bones. Even one of the most important bones in the body, the femur, can be cracked by a force of 4,000 newtons. Neo's force of impact is about 30,000 times larger than the average force it takes to break even the strongest bones in the body. With the use of physics calculations and estimations, we were able to disprove both the projectile motion and the free fall scene in the movie The Matrix.
This project has made it clear that physics is applied not only in entertainment, but in everyday life situations as well.